Okay, so good morning, everyone. Good morning, Dr. Jurgensen. Thank you very much for being here today with us. So, welcome everyone to episode 5 of Loops. So, for all those that are new to this initiative, this is a live webinar series that wants to highlight the innovation produced by the Horizon 2020 funded project. I am Daniela Bruccoli. I'm the communication assistant at Velta, and I'm very happy to be here today. Today's episode is going to focus to address another issue, another aspect of the innovation that's going on in the research environment nowadays. And it's going to be focused on the design of smarter composite materials and possibly the reuse of recycled ones. So I really would like to give a warm welcome to all of you for watching. I would like to welcome Dr. Jurgensen for being here. And we are going to talk about this issue with the contribution of the DACOMAT project and possibly the FiberEUse one, but the project coordinator might have some technical problems, so he might be joining later on if we've solved them. So now we can start. Before entering into the heart of the conversation, I'd like our guest to introduce himself. So please, Dr. Jurgensen, you can go on.
Okay, thank you, Daniela, and hello, everybody. My name is Jens Jørgensen. My daily work is as a research manager at SINTEF, the Department of Materials and Nanotechnology, where my focus is composites and polymer materials. And then in addition, I'm coordinator for the European project, it's 2020 project, DACOMAT, damage controlled composite material, which has been ongoing since 2018. Well,
Okay,
I'm happy to join here. I hope that we get a visit from the other coordinator, but besides, we just need to talk the two of us and the audience.
Yeah, it's still going to be a very interesting conversation. And now I just would like to give the audience a quick overview of how this episode is going to be. So our project coordinator of DACOMAT, Dr. Jurgensen, is going to talk about his project and his works and results they've achieved so far. And after that, we're going to discuss about it with questions from myself, questions from the audience. So I'd like to hear the audience's voice about this. And feel free to ask as many questions as possible below the YouTube live streaming or on the chat in the event page in LinkedIn. And we'll pick them up at the end of this discussion. Yeah. So now, I'll give the floor to you and the presentation of the DACOMAT project.
Just a question, Daniel. Will the audience be able to talk, or will they pose the question as in the chat here?
They can write questions in the chat in here, but they can also write on the LinkedIn page, and I can monitor it, and then I'll pick the questions and we can discuss about it.
Okay, yeah. Just so I know how it works.
Sure.
Then I will have to share my screen, I guess, in some way.
Yes.
Share screen. Okay.
Let's see. Okay, I can see it.
You can see it?
Yes.
Good. Then I put you on another screen. Okay, should I put it in presenter mode?
Yeah, sure. Oops. There's been some problems. I apologize for the inconvenience. Hello?
Yeah, it seems like when I
Yeah, let's try again.
can you hear me?
Yeah, yeah, yeah.
Okay. When I put the presentation in presenting mode, I lost connection. So maybe I should just keep it in.
Just
Keep it
yeah,
like
resize it to the full and then
yeah. I do it like that. And you see it for the moment.
no, just share it again.
I share it again. Yeah. Okay.
Okay.
So now you see
Now
my
I
PowerPoint client.
yes.
Yeah. Okay. Then I don't put it presenter mode. Okay. I will give you a brief introduction to the DACOMAT project, damage control composite materials, which has been ongoing since 2018, and we were supposed to wrap up by the end of this year, but as many other projects, we have got delays due
Sorry,
to.
I'm so sorry to interrupt you, Dr. Jurgensen. Just one
Uh,
second, because Dr. Marcello Colledani is here
oh, splendid! Yeah.
as well.
Good morning.
Good.
Sorry, I was closing the other meeting and jumping here. So I was presenting DG Prime in the other meeting.
Okay, no worries, no worries, it's fine. So, we just started to run this episode. I really welcome you. Thanks for joining us today, and we were just talking about the DACOMAT project. So, I just would like to introduce the audience with Dr. Marcello Colledani, who is the project coordinator of the FiberEUse project. And now I just updated the audience about what is going on. So now Dr. Jurgensen was starting to deliver his presentation about the DACOMAT project. And then I'll give the floor to you, Dr. Colledani, to talk about the FiberEUse one. Okay, so I apologize for the inconvenience. So Dr. Jurgensen, you can keep going.
Yeah, I think I would just say I will need to leave 12 sharp, so I've tried to make it fast now since we are delayed, and so we have some time for discussion also. Okay. Well, just composites. I guess many of the audience know that know about composites, but they are a preferred material in many instances due to their pros, which is they are strong, stiff, light, environment resistant, and has a large freedom in shape. Anyhow, they also have some drawbacks. If you have cracks in composites, they can grow, initiate and grow from imperfections and damages. And production imperfections cannot be avoided to some extent for large complex part. And there are also some color uncertainty in damage tolerance and residual life. So if you have a damage, it's a problem to know what is the remaining capacity. And this is some of the drawbacks that DACOMAT will try to reduce. So our objective is to develop more damage tolerant and damage predictable low cost composite materials and structures and technology to monitor and assess damages in these. So we are talking about rather rough composite materials like you have in wind turbines or blades or pipes, or could be in buildings, so large constructions. And what we aim is to make materials with high tolerance for manufacturing imperfections and a high capacity to sustain damages. And this should enable that the composite structures can be manufactured and maintained at low cost. And also the maintenance is also an important part of or the whole life course is an important part of this. And to achieve or to address this task, we've gathered a consortium of partners from the whole value chain. So material producers, engineering, research, end users. And also certification bodies like DNV, GL, and JCH performing life cycle analysis is involved in the project. And well, the project is structured like many other projects, work package addressing materials development, testing, modeling, structural health monitoring, and structural design and testing, and not at least life cycle analysis and recommended practice. We have realized really also that this with making recommended practices and how to say guidance on how to exploit the result is an important part of a project. Now, since this is a webinar concerning loops, so the circularity and lifetime of composites, has to add some points on the impact on composites sustainability, the impact from the results in DACOMAT. I mean, first of all, it's a longer lifetime of components. That's also an important part of circularity, that a product should last as long as possible, and so the material is used to the largest extent. So in general, more durable and components with longer lifetimes. But then we target materials and structures that should be easier to monitor the structure and detect damage before they come to a critical level, so you can actually repair instead of discard. And also, we through the modeling and monitoring research, so development in these areas, we will improve the means for assessing remaining useful life. It's actually it's a challenge for composite structures that they're typical designed for a certain lifetime, say a turbine blade, wind turbine blade for 25 years, or a pipe for 50 years, and then after that they should in principle be discarded and replaced by new ones. But many operators, owners, they want to challenge this, so use the structures for longer time, and in many cases the structure actually have a much longer lifetime in practice than what they have been designed for. And but to take that step, you need to have knowledge about the material and structure and how it actually behaves mechanical wise. And another issue is to obtain less discard due to production flaw and transport damage. If, say, you have a structure and become damaged or has a flaw, you should be able to live with that by having a damage tolerant structure. And also, by using composite materials in some construction cases, you can achieve a better levelized, let's say, lifetime cycle ecological footprint. For instance, by lightweight bridges you can install fast, avoiding large traffic diversion and longer times, and constructions in very harsh environments, which with other materials would have a significant lower lifetime. Well, the project is damage controlled materials, composite materials. So you might wonder what that means. One of the issues is damage tolerance, and I'd just like to define what we mean by that. For us, it's the ability to sustain damage or flaws permanently or for an adequate time period until repairs is possible, for instance. And to have that property, it requires that cracks are arrested or develop slowly or controlled. And then if you take it to the next step, what would be a damage control composite structure? It's a structure where the hot spots in the structure where damage will initiate is chosen by design. So you kind of know your weakest link, and these hot spots or weakest link, they should be designed to be damage tolerant. And this damage, and eventual damage tolerant at such a hotspot could be applied drop, for instance, in a composite. They should be say easy to monitor, and that also requires that cracks need to be stable up to a certain size beyond the detection limit of say your structural health monitoring approach. And the damage criticality should be able to be assessed with mechanical models, say fractal mechanical models. And as well, I mentioned already, the benefits from this is it's easy to have condition-based maintenance, reliable assessment of residual capacity and lifetime, and also in the design of certainty for lower safety factors, which actually again could save material and give lighter constructions. So what is our approach to achieve this? First of all, we consider laminated composite materials, so made from fabrics stacked and infused, and we consider interlaminar fracture resistance. So we have produced materials with a high interlaminar fracture resistance that raise with crack size. So when the crack size increases, the fracture resistance increases. And this we have achieved by making materials that has good properties with regards to generating so-called fiber bridging, which are fibers going from one fracture phase to the other. And in addition, we have we're looking at the concept of multiple cracks, so close parallel cracks, which can actually, if you have close parallel cracks, they increase the overall fracture resistance. A little more about that, the technicalities. If you have, say, what does actually make a crack grow slow? For a crack to grow, first of all, you need to, if you look here on the left figure, you need to deform a crack material, and that requires energy. And that energy is taken from strain relaxation in the whole structure. And if you have a crack in a composite without, say, a laminated composite without any fiber bridging, the energy that will be dissipated for the crack to grow, that's deformation of material in front of the crack tip. If you have fiber bridging, you will in addition need to dissipate an energy by, say, cracking, deforming, destroying materials, wrapping out the fibers in a longer zone behind the crack tip. So you have two areas where you need to where energy is dissipated that you need to overcome. If you then in addition have multiple cracks, you can add those together. So two cracks growing closely in parallel will require more energy than one, and by that you have a higher fracture resistance. Because nature have to some degree demonstrated this already. If you look at wood, you see like a big timber pile that I've been sleeping under. You have cracks with say fibers bridging, and you can also imagine, say, if you try to break some kind of a tree, and you see those multiple cracks holding this tree together, makes it very fracture resistant. So what we want to achieve from that is that if you, for instance, have a composite that is subjected to cyclic load, if you have one material which with no fiber bridging and say by that no raising fracture resistance with crack size, you would experience that as the number of lows increases, your crack size or length will just extend. If you have some degree of fiber bridging and raising fracture resistance, your the crack growth will slow down in time. And ultimately, if you can really make your material behave so you get multiple cracks and fiber bridging, you could ultimately make the cracks arrest fully. Well, just and well, as one of the results from the project so is that we made materials, resins and fibers with improved properties toward this behavior. And for now, we made as a first generation small scale demonstrator as a composite with ply drops, one with standard materials and one with DACOMAT materials. And we subjected to the same load for a certain number of cycles. And here the arrows indicate the length of the crack growth during a certain number of cycles, which is then substantially lower for the reference material than for the newly developed material. And if you are into mechanics, you can also see here we have a laminate with different thickness, so you get different loads for this different decreasing load at this end compared to this end. So here the total crack growth is slower, and it goes the same for here. Well, then in addition to, as I mentioned, material with improved interlaminar fracture resistance, as shown in the other pictures, we also develop improved simulation models for crack growth, which can be used in engineering or eventually, potentially also in the future for damage assessment, if you have the right materials properties. Improve probability of a detection in structural health monitoring, in particular with fiber optic sensing. And we're also working on recommended practice for materials and design for damage-tolerant composites. This is in preparation and one of the activities that we have focus on for the moment. Well, thank you for your attention. Then welcome any questions.
Thank you very much. It's been very interesting to receive this insight into the technicality of the project. Looking forward to discussing it later on. I'll first give the floor to Dr. Marcello Colledani to introduce us to the FiberEUse project. So please, the floor is yours. You can start.
Okay, so thanks, and very interesting project. Sorry for jumping in a bit late, but as I said, I was busy with presenting another project in another meeting. Okay.
No problem.
I'm sharing my slides now.
Yes, 1 second.
Please tell me when you see
Here they are.
Okay. Is it in full screen?
Yes. Yeah. 1 second.
Good. So,
yeah.
Good. So my name is Marcello Colledani. I'm professor at the Mechanical Engineering Department of Politecnico di Milano. And I will give you a little bit of introduction to the approach and results of FiberEUse project. The FiberEUse project is a large-scale demonstration project for demonstrating new circular economy value chains in the composite industry, so focused on composite materials. So we... yes.
Marcello, excuse me for a second. It's not in full screen. Could you see whether... Okay, perfect. Sorry to interrupt you.
I always ask because the two screens are different for different tools, but nevertheless. So we have heard from the previous colleague the motivation, but I will give you our core motivation while launching this project now 4 years ago. Of course, we concentrated on composite material, both glass fiber reinforced plastic and carbon fiber reinforced plastics, and with the goal to find sustainable routes for reusing the residual value and properties of these materials with a cross-sectorial approach, trying to solve a big problem that is becoming very serious and very pressing in some sectors. Of course, these materials are very interesting for specific properties that my colleague has just presented, but they also have this big challenge of being recycled, reused, and possibly with added value solutions. What is the current limitation? Well, there are several reasons for this recycling being complex. We thought that one of the main limitation is the fact that there is a lack of systemic and systematic value chain integration approach for reuse of composites. So companies in different sectors don't exchange too much of information about their specific requirements for the materials, and this somehow prevent for using the residual properties from one product into material for meeting the specification for another product. Of course, there is still poor customer acceptance for products that embed reusable materials, and in general, the high unpredictability and instability of flows of post-use products, of course, challenges the continuity of the circular value chain. Our approach in FiberEUse was very much focused on two key sectors, aeronautics and wind energy systems as input sectors. I think that these problems are very well known, especially for wind energy systems. So there is a huge amount of glass fiber coming from end of life post-use blades expected. We are talking about 70,000 tons in Europe by 2025, which is basically tomorrow. So at the moment, there's no stable solution for treating this material, and the only real and of course poor but real solution is landfill, and some countries this is not possible anymore. So we are really putting our effort in finding solutions, products, demonstrators to animate and activate a demand for this material after, of course, opportune treatments. This other graph is dedicated to carbon fiber reinforced plastic from the aeronautics, but the situation is not identical because, of course, the material is different mainly, and with different strategies as well, but still the search for a solution is pressing. As I said, our approach is cross-sectorial. I don't want to spend too much time here, but the main intuition is that since the starting specification for composite material in different sectors largely different with respect to the mechanical property of the products where this material is embedded, of course we can think of reusing materials from an high-end sector as a new material or a reconditioned material for components in another sector. For example, from aerospace to automotive, or from wind energy to sport equipment. There are links that are possible, of course, after suitable treatments. This is FiberEUse. So it's a large-scale project of 21 partners in 7 European countries, both companies and RTOs, research centers. And the project received funding for about 10 million euros, and the project is now in its last year. So we have several demonstrators, like the one you see just behind me. It's not that I always bring skis in my office, but yeah, I use them for demonstrating and give you a little bit of practical hints on what we do in the project. I would like to avoid extending this introduction too much, but I would like to give you just a few hints on the real demonstrators we are developing, because the project will be ending in September this year, and the still open points, and of course, a little bit of hints on the technologies we have been developing. we are, as a project, focused not only on innovative technology. We have innovative technologies, some of them are under patenting, but we also consider since the very beginning the establishment of innovation and innovative strategy for networking the stakeholders. And this is giving origin to our first version of the FiberEUse cloud-based platform that has the goal of exchanging information along the value chain about materials and possible reuse options of the materials. As we will see later on, this was the first brick to start the preparation of the DigiPrime proposal, that is even larger project, clearly focused on this digital platform that is currently ongoing. Just few hints on the three strategies we are following. So the first strategy that is giving origin to these three demo cases is basically based on mechanical size reduction processes. So we take the post-use component, we shred it, and we form a continuous and homogeneous stream of granules of glass fibers and resin, and we then reprocess this fraction into new products that embed this fraction plus virgin resin and virgin fibers. So with this strategy, we have produced these sanitary products, bath-use and shower trays with a spraying technology, and with at least 40% of recycled material inside. We have another demo case which is basically focused on, is triggered by Design Austria and Riveraska, and this is targeted to the production of design products. So very high added value, but low volume, clearly. Products to be used in the office furniture industry, for example, or urban furniture. And then you see the skis behind me. Yeah, this is the third demo case that is owned by HEAD. HEAD is willing to produce skis embedding recycled materials obtained with this strategy. I will jump directly to the second strategy, which is more traditional for carbon fiber, although we are innovating the process we are using for obtaining reusable carbon fibers cleaned. The strategy here is to use thermochemical processes, basically pyrolysis. It's not the usual pyrolysis. We use environment control pyrolysis with addition of gas that makes the pyrolysis more efficient and give the possibility to recover both the fibers and the resin. We apply this strategy both to carbon fiber components in the automotive industry. Here we have Meyer and Batz that are producing their demonstrators, and in the construction industry targeting glass fibers, long glass fibers in the roofing application. The last strategy, the last use case is a bit more futuristic in the sense that we are looking at electric vehicles. In particular, we are looking at developing, producing modular structures. We are focusing on the battery case, for example, and the platform, where components can be made of carbon fibers, can be disassembled, tested, repaired, and reused for other applications within the same sector, in the same type of cars. So this is more closer to the remanufacturing principle, where you don't actually go for the recovery of the material, but you look at recovering the function of the components, so the component itself. Here we have two German companies that are creating the demonstrators, EDAG, that is working more on the structure, the car structure, and Invent, which is focusing mainly on other components, and the component that is most interesting is this seating structure that is removable from the platform by using the patented solution for reversible joining systems. And of course, I cannot say more about this because the patenting is ongoing. So again, not too much time to give you more hints. I will only give you probably one hint on a technological solution. That is this one related to the disassembly strategy of the components. Of course, when it comes to disassembled blades from wind energy systems, you have problems. in managing the materials, and transporting the material is very expensive. So clearly our use cases, our demo cases need to be sustainable from both an economic and an environmental point of view. So we are giving great care to the calculation of the cost model in order to make the business case doable without external incentives, but based on the benchmark towards the cost of the virgin materials. Most of the demo cases are proven to be sustainable, and that's the good news. Of course, for the others, we are still working on improving the economic sustainability. But of course, to get there, you need to carefully evaluate the concentration of the fibers in the input components. And I tell you, in blades, is not homogeneous. So if you take a part of the blade, which is close to the rotor, the concentration of fiber is completely different from a part of the blade that is far to the rotor and is close to the edge. So if you want to reuse this material, you really need to start from the demand of the reusers, of the products that embed the reusable material, and pool the demand and adapt your process in order to obtain a stable fractional material meeting that requirements. So this demand-driven concept we elaborated during the project and was giving the origin to a Green Deal proposal that we submitted end of the last year, well, beginning of this year. Yes, so that was already embedded somehow in the FiberEUse concept. So it's important to understand the concentration and the type of fibers embedded, in each section of the product, and to consider the cost of the on-site treatment, of the transport, of the implant treatment, and of course all the administrative costs, in order to find a model for minimizing these costs. For the application in wind blades, we have developed this software that optimizes the cuts that the dismantler has to do in order to obtain as much homogeneous as possible flow of materials for the treatment and minimizing the cost. So you see that the cost variation is between the worst and the best scenario is quite considerable. We are talking about more than 10% of the cost that can be actually reduced if you use an optimized approach, demand-driven optimized approach. You see some samples that we treated. So we did a lot of experimental activities, a lot of production activities to get there. Of course, the size reduction processes are very important and they need to be controlled to obtain a mixture that meeting the demand. Again, I don't have too much time to go in details, but this is the kind of fractions that we obtain, for example, to develop the shower trays. We are going to very, very fine particles that can be sprayed on the component. We have produced guidelines for demanufacturing. These are quick, so if you are interested, just send me an email. I will share with you this document that will also be uploaded on the FiberEUse website. And I would like to conclude with a few more hints on some demo cases. Probably we already commented about this spray layup we use for the shower trays. This is a typical case where we have high volume. So it's extremely interesting for, absorbing a high fraction of end-of-life products and materials. Here you see some of the demonstrators for the design demo case. We are having this material, which is patented by Riga-Raska, and is very good for application in the furniture industry. Think of a top, or for application in other design products like this wine cooler that was designed by an Austrian designer in the project. And we will bring most of these prototypes in the Design Week event that will be done in Milan. This was already predicted for 2020, but it was clearly cancelled for the COVID emergency. It will be hopefully done in September this year in Milan. Just to conclude with the skis, since I have the samples here. So where do we act on the skis? You see HEAD has developed this ski. I don't see my camera, but I hope you see here, there is a layer of internal material. This is usually glass fiber reinforced plastics with virgin glass fiber. We are substituting a part of the virgin glass fiber with the recycled glass fiber, and we are already testing the functionalities. And you see, it's actually very good. So this demonstrates that recycled material can be used properly in products that are demanding products in terms of performance, high performance products. And so if you do a careful set of activities, a process chain, you can still protect and still preserve the high-tech performance of the product, and giving also this sense of sustainability, concrete sustainability to the customer. Yeah, I would like to close here. This is an overview of the installation that we will be doing in the Design Week. So if you are in Milan in September, please come and visit us at Super Studio Più. Thanks a lot, and sorry if I extended the time.
No worries, no problem at all. It's been a very detailed and insightful presentation. Thank you very much. So now, while we wait for questions from our audience, I'd like to ask you, is there some kind of curiosities or doubts that you would like to ask the other project?
Well, I have one question. You showed this approach for the automotive industry, where you have components which are designed to be dismantled, and then you test them, and then you can use them again. How do you perform the testing in a, say, non-destructive way that do not reduce the remaining capacity of the component?
Yeah, it's a very important point. I've seen in your project you have Strathclyde University as a partner. Strathclyde University is also a partner of our project. They have been developing a non-destructive testing activity using hyperspectral imaging. So for the characterization of potential damages on the surface. Of course, hyperspectral is interesting technology for vision-based technology for, of course, surface defects. It cannot investigate really in thickness defects, so inside defects, but we concentrated on surface defects, and the results are pretty encouraging for further investigation in this direction. But I think this point could be a very good actually touch point between the two projects, because
and this inspection, it is intended to be performed on each component for each car, so not just as a
yeah, the idea is that exactly. So EDAG that proposed this strategy is developing solutions for the long-term vision of automotive industry, right, for the future. So they are really looking ahead. What they have conceived as a concept is this idea of taking the car, for example, from the rentals from the this kind of electric vehicle city car sharing systems. When the components are damaged, you can disassemble easily the component from the structure. You can test it, and each component should be tested, of course, with a 100% approach. And of course, it should be fast. And then where you see defects, you can repair the defects. So we have been working on a laser-based repair on top of other strategies, more common, more traditional. And then you can reassemble the component in the same or other structures. So this is the idea of standardization and modularity in the component geometry.
Thank you very much for answering.
I also would have a question, a curiosity, because I see a lot of complementarity between the two projects, and that was very interesting to see the slides. So in terms of monitoring, I think that you have not directly focused on wind energy, but it was among your demonstrators, your cases of references. And have you thought about, I'm sure yes, but probably how, about using embedded sensor more widely into these blades for characterizing the material? And second question, second curiosity I would have, how would your new concept of materials actually behave at the end of life in terms of reusability of materials for second life application?
Well, in terms of monitoring, of course, one of the general challenges for instance, wind turbines, monitoring wind turbines, is it's a very large area. So our approach there is also that you should be, by designing your structure in a way so that you actually choose where a crack or damage will initiate, and you make that area damage tolerant, then you should be able to reduce the total area that you need to monitor. So you could focus on those areas where you say, okay, if your structure is subjected to an overload, a high load, this is where a damage will appear, and then you can monitor that and you can follow it. Is it stable, or is it severe? Then you will need to say stop loading your asset and go for a repair, or in the last case, or the ultimate case, a replacement. But of course, it's a way to have that implemented in wind turbines, but it's a philosophy, and the technology is maturing. With regards to recycling, we haven't addressed recycling particularly. So the only the only thing making our materials a little more prone for recycling is that we are focusing on polyester and vinyl esters, which are, in sense of chemical recycling, perhaps more forgiving than epoxies. But there's also development in that directions for epoxies. But definitely there's also a need for going in the wind industry, for example, or in the larger composite construction industry, towards an approach where you can disassemble and get out mature components, or no, not mature components, but valuable parts. There are really many wind turbine producers now starting to use pull through the carbon planks, for instance, which, if they can be retrieved, they could have a high value for other purposes, or maybe even for reuse in a wind turbine. But besides that, as you also pointed out, one of the very important issues with composite recycling is that you cannot expect a wind turbine blade or a car necessarily to be recycled into the same product. Yeah. In most cases, it will go from one product to another product, and from one business to a total another business. So it will require communication and planning between businesses, which has not been in the past.
Yeah, totally agree. So this is the big challenge. Definitely. Very interesting. Thanks.
Okay, thank you very much for this exchange. We have a couple of questions from our audience. So the first question, they're both from Paloma Rodriguez, and she's asking, which is the manufacturing process used for the skis, for instance, in the case of the FiberEUse?
Well, it's a bit part of the knowledge of head. So we have been visiting, of course, then we have been established there our demonstrator, and I'm thinking what can I say? Is basically, what can I say? It's a little bit, in a doable way. It's a layer product, right? You see many layers, and I think also in my slide was seen that clearly it's a layer production, and I don't know what can I say. So I would suggest for you to visit the website, and we are uploading there all the information that can be disclosed. So you would understand that, of course, we cannot discuss too much in details the specific process chains of the manufacturers in this project. But you will find quite a lot of public information over there. So I'm sorry, I cannot be too detailed now without the permission of the company, as you may understand.
She's also asking, have you tried additive manufacturing for any of the demos?
Oh yeah, sure. That's something we tried. We are developing at Polyme, and it's very interesting. So we are developing now virtual library. It's called. It will be a part of our website, where you would be able to see the appearance and the properties of the material. So you will see a lot of components done in additive manufacturing. It's very interesting. Of course, advantages of additive are known, so shape, and clearly you can obtain very complex objects. The complexity is now understanding the functionality of these objects. So why should you do additive manufacturing for developing these components, and what is the functionality given to these strange shaped components? But the results are really interesting and relevant. So I invite you to see. It will be uploaded in 1 month. You will see this virtual library, and you will appreciate the developments in this area as well.
Okay, thank you very much, Dr. Colledani. I have a question for the DACOMAT project. I was just wondering, will the new formulation of the composites have a higher impact on the environment initially, and then will have long-term benefits?
I mean, the production of the material itself will be, in terms of environmental footprint, more or less like now. So the impact and the benefit is more in the gate to cradle phase. The gate to grave or to recycling phase. So in the service life, improving the service life in general, and reducing the cost for maintenance.
Okay. Yeah, makes sense. Okay, so an additional question for both projects. What would be the barriers or aspects that would affect the commercialization of these composite materials? Would you expect to require something from the current legislations? Would you like to change or?
I mean, say for DACOMAT, for instance, the materials they can be commercialized with the current legislation. See the utilization of the concept of damage tolerance and damage control, so say, is more relying on having good standards and guidance. So how to actually design such a structure, how to test the materials, how to qualify them, what is the effect on safety factors, and so on. So having a not too complicated guides for industry that they can use to do this on, say, different levels. Because you can make it really difficult with modeling and so on, where the answer pros, but that's not always feasible for industrial use.
Of course.
Well, what I would add here is that I think that there is a lot of attention today on plastics, and plastics from packaging, from consumer goods. Composites are important. So composites are really important, are widely adopted, are available in many products of common use in B2C and B2B industries. So in terms of volumes, are very important. So they should not be considered as less important as plastics, as it's considered in general. So that is my first message. Of course, because the polymeric fraction is there. So I mean, there's a important implication on the environment and on the possibility of reusing this material if we don't do anything with this material, this type of products. The second issue that I would like to raise is that, of course, these cross-sectorial reuse options are possible if you adopt an end of waste principle, right? So if you transform something that is classified into waste into materials that can be classified as resources. And of course, you have some procedures, right, to make reference to this end of waste principle. We are currently at Italian level trying to go through these steps to get these materials certified for use. I cannot tell you yet if it's difficult or not. So we are just started with this as a sort of last mile of the project before the industrial uptake. But yes, this the maturity of this end of waste principle should be increased probably in order to make these business cases possible at industrial level.
Yeah, thank you very much. That's a very good input. Okay. So we don't have any further questions from the audience. So I'm just going to wrap up, and I would like to really thank you both for your contribution to this episode, and thank you very much for participating. And I wish you a good day, and I'll see everybody in the next loops. Thank you.
Thank you for the opportunity, Daniela, and I would like to keep in touch with both of you. Okay, thank you.
Yeah, sure. We'll keep in touch by email.
Yeah.
Bye-bye.
Jorgensen, bye-bye.
Bye-bye.
It was a pleasure meeting you.